people out there who have listened to dozens of my videos, but have no idea what I look like. So I hope I won't disappoint them too much, or scare them too much. Okay, so ladies and gentlemen, this take-home exercise was one which drew actually on the previous one. In the previous exercise. Okay, sounds like audio is working. Thanks. In the previous exercise, I asked you to create a differentiation operator. So the hallmark of that operator was that it was an operator on functions. So it was a higher order function in the sense that both that it took in a function as an argument and it returned a function as a result. The function it took in was a unary function, a function of a single variable, x, say, and it returned a function that was the derivative of that function applied with a certain level of numeric precision, and that function could be then given a particular value of x at which to take the derivative, which to assess the slope of the curve that was originally passed in, and it would report the slope of that line of the curve at that point, right? So that was what we did last time. It was a derivative operator. Took in an argument, function, single argument, and returned a function of a single argument, where the thing that returned was the derivative of the function that it passed in. So this time I asked you to do something related. It's kind of, in some sense, the inverse of that. It's an integration operator. So once again, it's higher order in the sense that it takes a function in and returns a function, both of those. But the function it returns is the integral of the function it takes in, right? Integral between two points, integral from a starting point to an ending point, right? So it's a definite integral, and it's numerically integrated. It has a certain value of dx, of sort of the granularity. And I asked you, for the sake of this, to kind of put aside some important considerations involving numerical error and numerical analysis, and simply make use of a simple integration scheme. And I may have to ask you to use your imagination here as much as to look at the board. And unfortunately, those out there in internet land, I'm actually not looking at you. I'm looking at the sort of thing on the board, and I can't see a trace of it. Could anyone run to one of the rooms and see if there's a marker there that's a little bit better? Don't interrupt any sort of meetings going on. So the truth is, my boot camps have provided these rooms with much of their supply of markers, but it's only refreshed at the time of our boot camps, and so it's in the summer. So these things tend to run down during the year, and then we bring a new batch, and that's my bequest. If anyone else can see one. Okay, so we have a curve here. We have a curve which is depicted, and I'm asking you to integrate that curve, to create an operator which will integrate the curve from a certain starting point along the curve. I'll call this x start. X start, okay. Oh, no, we're doing a little bit better. X start to some end point here, x end, okay. X sub n end. Okay. You get the point. And I'm asking you to then integrate it with a certain granularity of numeric precision. And so there's going to be a certain dx that we use to integrate this. And we're going to have evenly spaced components at a spacing of dx. And one of the key realizations here, oh, wow. Okay, Iman saves the day. The cavalry has arrived. Okay, okay, thanks. Oh, wow, that isn't even from our boot camp. Okay, so here's x start, and here's xn here. And then we have these regularly spaced sort of points for integration along here. And maybe for clarity, I'll put them as coming down from this line here. Okay. Just like that, right? When they cover undergraduate calculus, they don't cover the side effects, but it's helpful, like the sound effects associated with calculus. But it can be useful to consider them. So each of these is of size dx in terms of its width. And I asked you to use a particularly simple scheme, which is called Euler Integration, after the famous mathematician Leonhard Euler, which basically approximates the total as a sum of rectangles. And you can do a lot better with triangles and fancier schemes and taking the midpoints and that sort of stuff. But to keep the code simple and to focus on the higher order functions involved, currying and enclosures, I asked you to just consider this simple scheme. So the idea here is that this function, which we'll call, without loss of generality, f, this function whose integral we're taking, here we go, f. Okay, this is f of x. Yeah, I could see something in there. Okay, that function f of x, whose integral we're taking, we're going to sum up these sets of values. So at a given point x, the value of the function at that point will be f, at this x location. So here we are, say x start, and the area in that rectangle will be f at x start. That's the vertical component here times dx, right? Because it's of width dx. So that's the area, right? There for that rectangle. And similarly, the area of this next one will be f at x start plus dx times dx and so on, right? We'll be summing up. And all is nice and good until the final one. And at the final one, the plot thickens at this one because we might not have a full rectangle, right? And so there's some finesse needed for this final one because the full rectangle might not fit into it. We might only have a sliver of a rectangle as we do here. And so we won't have a full dx necessarily of width, right? This is a fairly crude approximation as far as integration is concerned. But if we're doing things at sufficiently small dx, it might be an adequate representation because we're not getting too much change in the height of the function between these points. Okay. So this is the general scheme that I asked you to outline, or that I asked you to approach in code. And the emphasis here was not on the numerical analysis or the math of it, but rather on the software engineering and in language sort of linkage here. Okay, so we're now going to transition to one solution to that. Okay, so I'm going to reveal my solution, and I want to, in order to cover this, I want to actually emphasize a few things about Scala. And for this, I'm just going to use my my Scala shell here. So one issue that that is related to things I mentioned in the assignment, as I recall, is that in Scala there's ways of creating numeric ranges. Okay, two of the big ways that I want to emphasize are, you could say like 0 to 10, and it will create, in this case, these are integers. It will create a range of, including 0. And the key thing to note is that it's inclusive. So 0 and 10 are part of it. Okay. By contrast, and I want to emphasize this, actually will be very germane to that final, I am doing a disservice to our colleagues online. So let me just switch over to screen sharing. They've seen enough of my unpleasant visage. So I will now switch from my mean to online. Okay, here we go. I think everyone can see that now. So here we go. So switching to this, if you do 0 to 10, you get things inclusive here. If I do 0 until 10, I get everything up to but not including the last one. And as I said, this is going to be very important actually for that last data point. So forgive me for emphasizing. And notice with these, Scala is doing some type inference. How do we know it's doing some type inference here? Well, it figured out that these are integers here. If we had instead done, for example, this, right? Now it's got a numeric range of doubles, okay? And we could, more than that, we could actually say like by, 0.5 or something like that, right? And here's a numeric range. See that? Yeah. Notice it's immutable. Scala has a lot of collections that are immutable. Why? Well, amongst other things, immutable collections can be shared. You can share them without worry, right? Multiple things can reference them without the worry that any one of them will stomp on them, okay? So, ladies and gentlemen, we have here collections, and notice that this one includes that, but if I were to do until this, it does not include that last 10.0. It includes everything up to it, right? Even though 10.0 is a multiple of 0.5, right? And similarly, if I did 9.9 here, it does not include it, right? It does everything up to that. Forgive me for emphasizing this. It probably seems like an arbitrary bit of minutiae, but it will be highly important when we come to talk about how we handle that last data point, okay? And the fact that we have these partial rectangles represented. Okay, so I just covered those basics and those distinctions. Probably I should cover these things or copy these things into here so that you can use on them in the things that I post to the Moodle site. But let's go on and discuss more substantive matters. Let's talk about the integration operator. So, ladies and gentlemen, how would you implement an integration operator in Scala, and particularly one that allows you to have staging of the arguments passed? So you can take a certain set of arguments up front, like the function, to be integrated, but then separately you specify dx, the granularity numerically of the width of the rectangles, and then separately the values to start and end the integration. How would we do that? Can anyone say? What would we need to do at a very high level? What's one way of solving that problem? Sorry? Until. Yeah, you could use the until. Good. Good. And map the unary function. Good.
I used a function.
Oh, okay. Sure.
Summon the function by one.
Okay.
I didn't use that.
You could do that. Yeah, you could do that. That's another way to solve it. As we'll see, there's trade-offs in terms of clarity. This one will actually create sort of a set of items over which we could map the function. And each one that we map, we evaluate the function at that point, multiply it by dx, and we sum up the results. Now, Notice I call this naive because this is ignoring one very important fact. What is that? The last one. Yeah, that special last one. This is assuming that everything like xn is all evenly spaced by this, etc. But it communicates the essential features of the situation, right? We are evaluating, we're considering all the different points here, and I don't know that I should do this, but I'm tempted to try to serve my internet viewers here by including them in. So we enumerate each of these different x points up to but not including x end itself, okay? And then we are summing up for each of them the size of the rectangle as determined by Fn unary as evaluated at that point times dx, right? So we're not handling that final point well, which is going to include a partial rectangle, but we're doing a pretty good job compactly integrating the earlier components here, and it communicates the essential feature of the situation, which is we find out the x points, we evaluate the unary function on each of them, and multiply it by dx to get the rectangle size, and we sum up the results, right? It's straightforward, it's quite simple, and it is powerful. Now, what if this were huge? What if this thing here were huge? What if dx were like 10 to the minus 6 and x start to x end was over a magnificently large range, 0 to 1,000,000 or something? How well would this strategy work? Could you see a problem with it? Would it work? Yeah, it would work. What would the challenge be? It would actually produce here. I mean, if you go look at this, it's actually producing, yeah, a full collection of numbers. And we would map it, and that would produce another collection of numbers, which would be very large, very, very, very large. And only then do we sum them up. Okay. Now, we could do it. It's functional and it's clean, but it might run into memory issues in terms of storing all these things. And this is just a forward pointer to the latter part of today's discussion and the components of the book, which basically point out that if we captured this in a more savvy way, in a lazy way, where this was not computed until needed, we could actually do it in an incremental fashion. Rather than computing all of this, mapping all of that god-awful big collection to a new giant collection and using all the memory for that and then summing them up, we could actually do one by one all along the way. We produce an x, we map it to the evaluation of the function at that x times dx to get the rectangle size, and we add that to our running sum. We do it for the next one. And basically, we turn it from taking a giant collection and mapping it to a giant collection and mapping it to a sum to incrementally doing the whole thing with each little piece. We get an x, we apply this thing to the x, we add it to our sum, we get the next x, etc. And that's what streams, and that's what laziness will allow us. And that's the power, the beauty, and the significance of it for dealing with very large-scale data. You know, for dealing with data that's otherwise hugely large in character, we can perform our pipelines incrementally. But that's looking forward. We'll come back to that. I want to talk about how to actually do this to handle the final data point, okay? Now, ladies and gentlemen, for the final data point here, we're going to need to deal with the fact that the final rectangle here has to be treated separately, especially because it can only be of a certain size. Okay, and it may be very thin. It may be of the full size or anywhere in between, maybe of zero size. And we need to not only total up these previous ones, but we need to also deal with this final one. And I provided here 3 different ways of accomplishing that, of dealing with it. And the basic gist of how we're going to deal with it, and I've actually got to find out, I did this late last night, and I probably should have been more careful here with one thing. But the essential deal is we're going to sum up everything to this point and including xn, okay? And what we're going to do then is subtract off the element of that, the element of error that lies outside of xn, okay? And the realization here is that the last rectangle may extend after xn because it's going beyond the final point. Okay, so I think all of these actually, now that I look at it, should actually be 2. I'm going to have to double check this, but I believe that's the case. In any case, I provided a bunch of different ways that this could be accomplished. Okay, one way is by but all of them share the fact that they compute this total, including xn, including a rectangle that's based there, and then we subtract off the portion that's outside of xn. Why is xn so important? Well, let's switch back to the board here. Boom. Here we've got some of this rectangle from xn, which is, excuse me. Okay, no. These actually should be until. Sorry, I'm not thinking clearly here. So ladies and gentlemen, here's xn. We're summing up to the last data point just before that, and we're computing a rectangle of width dx. And the problem is that rectangle has some of it that lies inside of xn and some that lies outside. Okay, there's some of this that occurs after it because it's the data point, the x location just before plus dx is where this rectangle ends, right? And that last data point, x location plus dx may be greater than xn. So it's really this component here from this kind of outer part of this rectangle to xn. It's the area underneath that we have to subtract out. Do you see what I'm saying? Yeah. If we're doing so, I was right last night, and I was wrong to briefly change that over to 2. It's actually until here. Okay, great. So I did this in a bunch of different ways. There's some mathematics, and it's discrete mathematics associated with it. Discrete because we have a certain number of these rectangles. And so I use this operator ceiling, which, you know, if say xn minus x star divided by dx, if that supports, you know, 1, 2, 3, 4, 5, 6, 6.5 rectangles, you know, within it, the seal of 6.5 is 7. Okay, and I'm using that ceiling to basically compute here the location of the end of the last rectangle, and I'm subtracting off, or excuse me, the width of all the different rectangles, and then I'm subtracting off xn minus x start, which is the distance required. And I actually present this in several mathematically identical ways of capturing it, but I think the last one is the clearest from a software engineering standpoint. So I'd like to explain this last one. Okay, So these are the data points included. These are the x values included, okay? The x values associated with each of these locations. X start plus dx, x start plus 2dx, x start plus 3dx, all the way up to the one just before x end. Just before, that's this guy here, right? Okay, and that's what we got through that until. And so what I've done there from a software engineering standpoint is give it a nice name. And mumble, there we go. So I've given it a nice name. Those are the data points included, the x locations. So that's a bunch of x locations. Next, I take the last of them. That's the final rectangle starting point. That's the starting point of the final rectangle, right? That's this guy here. That's this one. The one just before x end. Okay. And then I ask, well, what's the height of that? Well, it's whatever the value of the function is at that point, right? And then I say, what's the finishing point of it? Like, what's the final x value of that rectangle, which often is greater than x end, and it's wherever it started plus dx. Okay, and that's where it goes to. And then I ask, well, how much of it is outside of x end? Well, it's that minus x end. That's how much of it is outside. So when I talk about this, and I'll go back for internet viewers. So here's the last data point. That's the starting location, last data point. The finished location is that plus dx. And I subtract off from that x end to get the width of this guy here. The amount of the last rectangle, the amount of x of the last rectangle that lies outside of x end. And of course, I can then go and subtract. I can multiply it by dx and subtract it. Oh, yep, there we go. And subtract it off here. So here's the width of the last rectangle, right? Or the area of the last rectangle. Maybe I should do val final rectangle area outside interval. Outside the integration interval is this guy here. And I subtract that off the sum here. Okay? And that allows me to have a total value. You notice that this is a function. That's why we have an equal sign here. It's actually a method, and the final expression in it is the return value. So this is the return value for it. Okay. So having done that, we can then integrate things. So to test this at an initial level, what I did is actually I integrated it for a constant. Okay, let me go define my, right. Okay, this is just complaining. So if I do this, I get back a function. This underbar just tells it essentially to get back a partially applied function. This partially applied function is the integration of a constant function. That's what this guy is, right? That's what fn unary is here. It's a constant function, okay? Constant because it's whatever the value of x is, it evaluates to 1. It's a partially applied function because I haven't evaluated these extra arguments yet. So now I'll give it an extra argument, 0.04. And if I ask for that as a partially applied function, now I've got a function which is going to take in a start and an end. That's what these guys are. And return back a double, which is the interval, right? So if I then go give it a start and end, and one of the nice advantages of doing this with a constant function is I don't have to worry what the start and end is. You know, all I have to know is their distance from each other. It doesn't matter if it's 0 and 1 or 1 and 2, as long as they have a distance of 1 from each other, the integral is going to be 1, right? And I can do this with different sizes of this. I could do it with a very small one, boom, and I'll get essentially the same answer. subject to numeric error. I could do it with something that doesn't fit neatly as an integration size, and I'll still get the same error. I could do it with something that's actually quite crude, and I'll still get essentially the same error because it's all flat. It doesn't. There's no change in this curve, but it serves as a useful sort of basic sanity check. And then for the request of the problem set, I define dx here. And here we go, over to here, paste, boom. And I defined a set of operators. By the way, in the Spark shell, you can do this, including in the one in Zeppelin, I think. And I can put these all in. So these are integrals of that function, of that function, of that function, and that function. And I can test them out by applying them to different values here, right? So I pre-computed what these should be based on principles of calculus. This integral of constant 1 should just be x. Integral of that dx is x. And so if I evaluate it between 0 and 2, it should be x at 2 minus x at 0. And therefore 2 minus 0 or 2. And if I do that, it's a happy camper. It's close enough to 2 for my comfort. And similarly for x squared, well, the integral of x is x squared over 2. And I get back an appropriate thing. And then I did 2x, whose integral is x squared. The value from 2 to 0 is going to be 4. And we're getting things that are subject to round-off error, but are decently accurate. And similarly with x squared, it's going to x cubed over 3. This is what we get. Okay, so that's our little large part of that exercise. I didn't do the interaction between it and the derivative operator. But in terms of testing, what could you do with the derivative operator and then the integration operator to test them? How could you test them together? Sorry? That's right. So you should be able to, if I apply one, if I integrate and then differentiate, I should get something that's the same as the original function. Sure, I should be able, with an arbitrary original function, confirm that numerically integrating it and differentiating it gives the exact same value as the original function, modulo a tiny bit of modulo epsilon integration error. So it provides for a very nice way of actually doing some random testing with things and trying it with different functions and ensuring that the two are compatible in their implementations. Okay? Numerical integration. Any questions about this example?
I didn't take the least square into consideration. I got the same answer, like
the last one.
Yeah, I didn't take all these calculations.
Yeah.
I got the same answer.
Right. So I did this guy first, and at first I thought, oh, that's good enough, and then I don't feel good doing that. And so last night I just did the full Monty. I just did the other things because I figured, okay, let me take care of that. And actually, it turned out to require some pretty specific sort of thinking about the discrete values and so on. But this is the cleanest way I know how to do it. Mathematically, this is more compact up above, but this is easier to explain to someone because the intentions are clear in terms of the naming, et cetera. It's just, it follows very logically through what's going on, including finding the last point that's being integrated rather than computing what its location is based on ceilings and so on. So, it's an interesting comment on the trade-off between mathematical sort of conciseness and transparency in terms of someone understanding what's going on. And when it comes to functional programming, you will find people in the functional programming sphere who tend more towards conciseness and others who tend more towards software engineering principles of transparency through good naming and naming intermediate variables, and there's kind of a spectrum of people there. Okay, so that's why I did it in different ways. But it will be almost exactly the same for certain cases. But if we were to do like numerical integration, integrator naive, let me just do this one right now, okay? Here's my numerical integrator naive. Give me something where it would actually be quite different. Can anyone say? What would be a different? That's something where we'd expect it to actually be quite different. Anyone? Well, okay, even with a constant function, if I did it, let's suppose with an integration value of 0.1, and I did it between that and from 0 to 0.25 or something like that, it's going to tell me 0.3, which is to say the least, rough approximation of that integral, right? Or if I were to do it to 0 to 0.05, it'll say 0.1, which lacks finesse. But if I were to say here, it does it right on the money, right? And same thing with this guy, because it sweated the final rectangle. Okay, so. You got the essential features of the situation probably in terms of a pipeline for processing it, but I couldn't stand before the class here and do it without dealing with the final rectangle. In my business, we have to sweat the final rectangles. Okay. Yeah. Okay. Good. Any other questions? Yeah.
I use recursive loop.
Yes.
What is the problem with that?
A recursive loop will be okay with the proviso that if you have a very, very long sequence, it could lead to a stack overflow in certain cases. Now, in fact, compilers are smarter than that, okay? And it turns out that the Scala compiler, I believe, and quite a few others out there for functional languages, they distinguish between two types of recursion. There's something called tail recursion versus non-tail recursion. Tail recursion is a situation where, like, A calls B, so A calls itself and keeps on calling itself, and as soon as one of the inner A's return, the next outer A can return, and next outer A, next outer A, next outer A. It doesn't do anything with the results after that. But it turns out there's a lot of cases that can be turned into tail recursion where it does something with the results by making it an extra parameter for A. So if you actually create an extra argument for A, you can actually do things that you wouldn't think are tail recursive, but you can render them as tail recursive. And it turns out tail recursive things, a good compiler will turn into a loop. And so it's expressed as recursion with the clarity that many of us see in that, but then it's actually implemented as just a loop without actually creating a stack frame and sort of initiating the variable with that and creating another stack frame and growing the stack. It actually does it as a loop. So in some cases, and I'd have to look at your example, in some cases it requires no extra cost and enjoys the beauty of recursion. But in other cases, recursion is not tail recursive. You can't render it into a tail recursive form, and it's going to build up a stack that's larger and larger. But, Iman, your solution is actually forward-looking, because this will not be our final encounter with integration. In this class, in this very classroom, not 5 lectures from now, probably not even 3, we're going to have another example based on streams of integration. And there, the recursive form of it is going to be key, okay? And it's going to be beautiful. And it's going to be powerful. And we can integrate it. We could just ask, tell me another data point. I can just integrate it out, give me another data point. And for integrating differential equations, this is going to be great because we could just say, okay, you know, tell me the next state of the system, tell me the next state, tell me the next state, tell me the next state of, you know, how many susceptible, infected, and recovered people there are. And it's just going to keep on giving me, let me integrate out the system over time. And there, the Imanian solution will be preeminent. Okay? Okay. Other questions? Oh, I can't wait to get to that. Okay. Okay. So, ladies and gentlemen, we will stop this and we will proceed now to other elements of the lecture. Okay.